Okay, picture this. You've got a bomb. And this bomb is so incredibly sensitive that a single photon, the tiniest possible particle of light, will set it off. Now here's the puzzle. How do you find out if that bomb is real without ever letting a single photon touch it? I know, it sounds completely impossible, right? Well, today, we are diving headfirst into one of quantum mechanics' greatest paradoxes, and a brand new theory that says it has the answer.
And really, that's the question at the heart of all this. How can you get information about an object? How can you know it's there without any kind of direct interaction? You know, the way we think about interaction. It feels like some kind of magic trick, but quantum physics suggests it might just be a fundamental part of how reality works.
So, to unpack all of this, we're going to walk through 5 key ideas. First up, the quantum bomb paradox itself. Then we'll introduce this new theory called entropicity. From there, we'll dig into its core idea. Constraint, not contact. After that, we'll see how it reshapes our view of reality to actually solve the paradox. And finally, we'll zoom out and ask why this might just change everything we think we know about the universe. All right, let's kick things off with part 1, the quantum bomb paradox. This is a really famous thought experiment that just completely messes with our everyday intuition, proposing a way to measure something that seems like it should be logically impossible. For years, the standard textbook answer has been this thing called quantum interaction-free measurement, or QIFM. And it's super clever. It uses wild quantum concepts like superposition, a particle being in many places at once, and interference. And it works. The math checks out. But it can feel a little unsatisfying, almost like a philosophical trick that leaves you with this nagging feeling that we're not seeing the full picture.
But what if there's a whole other way to look at this? Maybe one that's a bit more intuitive. This brings us to part 2, a new theory called entropicity. And it suggests that, actually, there is a kind of contact happening, just a much deeper and more fundamental kind than we're used to.
And you can really see the difference here. The standard view, on the left, it talks about interaction-free measurements and the mysterious wave function collapse. The theory of entropicity, or TOE, introduces a totally new language. Instead of interaction-free, we get constraint-based. Instead of just superposition, we talk about distinguishability and symmetry. And wave function collapse is replaced by something called entropic selection. It's basically a whole new vocabulary for describing what's going on.
So at the very heart of this new theory is a concept called the entropic field. Try to imagine it as the basic fabric of reality. But instead of being bent by mass and energy, like gravity, this field is all about possibilities. It literally maps out the differences, the distinguishability, between every single possible future, every possible arrangement of the universe. It's the landscape of what could be.
Okay, moving on to section 3. This is the absolute core of the whole theory, so let's really break it down. Constraint, not contact.
This quote right here says it all. The bomb participates entropically even when it does not participate energetically. So what does that actually mean? It means that even if zero energy is exchanged, no photon hits the bomb, no heat, nothing, the bomb's mere presence is still an active player in the experiment. It's still changing things. And how does it do that? Well, it's through this idea of distinguishability. So imagine you have 2 paths a photon can take, and they are perfectly, absolutely identical, symmetrical. But then you place a bomb on just one of those paths. All of a sudden, that path has a unique possible outcome, a massive explosion. That potential, that possibility alone, makes the 2 paths fundamentally different. They are now distinguishable, and their perfect symmetry is broken.
And that broken symmetry leads us directly to this next concept, an entropic constraint. This is the idea that any object, simply by existing, physically alters the field of possibilities all around it. Its presence acts like a rule, a new boundary condition that literally reshapes the landscape of what can happen next. It's not a physical wall, but a change in the geometry of possibility itself.
So here's how it plays out in 3 steps. First, you start with a symmetrical system. Think of our 2 identical paths existing in a nice balanced entropic field. Then, step 2, you add a constraint. You put the bomb there. Its presence actually deforms that field, but only along its path. And finally, step 3, that deformation is what makes the paths distinguishable. And that broken symmetry is everything. It changes how the whole system evolves from that point on.
Which brings us to section 4. Now that we have these new tools, constraint and distinguishability, let's go back to the original bomb paradox and see how they solve it by fundamentally reshaping our picture of reality.
Okay, let's walk through it. Step 1. Before the bomb is there, both paths are identical. Quantum interference works perfectly. Step 2. We insert the bomb. Suddenly, one of those paths carries a unique, irreversible consequence, the explosion. Step 3. The mere possibility of that explosion creates distinguishability, and that shatters the entropic symmetry. Step 4. Because that symmetry is gone, the delicate interference pattern completely collapses. The system just can't maintain it anymore. And now for Step 5, the magic. A detector clicks in a place it was supposed to be dark. That click doesn't mean a photon hit the bomb. No, it's the system telling us that it felt a hidden entropic constraint, and that proves the bomb is there.
So, with this new way of looking at it, the whole phenomenon gets a new name. It's not quantum interaction-free measurement anymore. It's entropic contact-free measurement. And that's the key takeaway, right? The contact wasn't energetic. It was entropic. The system felt the constraint that the bomb's existence placed upon it.
So let's just quickly recap the foundational principles of this theory. First, distinguishability is what really matters. It's the main driver of physical effects. Second, a measurement isn't some weird magical event. It's simply the act of revealing a constraint that was already there. Third, that mysterious quantum collapse, that's just the system making a logical choice, an entropic selection based on the new landscape of possibilities. And finally, there's a fundamental trade-off. You can't have both distinguishability and reversibility. Once the bomb makes one path different, the original state of perfect interference is gone for good.
So, what's the big deal? Why does this all matter? In our last section, let's just zoom out and think about the bigger picture. Because if this theory is on the right track, it could totally shift how we think about everything from quantum computing all the way to the nature of cause and effect itself.
And if you take away only one thing, let it be this. This is probably the most profound statement in the whole theory. Possibility is physically active. Now, that's not just a cool philosophical idea. It's a claim about physics. It says that what could happen, the potential for the bomb to explode, is a real physical feature of our universe that has tangible effects, even if it never ever happens.
So, the bottom line is that in this theory, an object's existence is not a passive thing. Just by being there, it creates what's called an entropic boundary condition. It actively reshapes the universe of possibilities around it. Just existing is an act of participation in the cosmos. And that brings us to one last kind of mind-bending thought. If an object's mere existence reshapes the entire landscape of what's possible around it, then what is your presence? You, just being here right now. What is that changing in the universe?